going to go through here is we're going to be talking about energy. Hopefully you've done the energy skate park where you worked with, we're on the path of the skater on that little roller coaster like track. Did they have kinetic energy and potential energy, and look at either the location or the motion of those places where they had lots of potential or kinetic energy, because we're going to be building on that knowledge here. So first off, let's talk about what energy is. This is a word that gets used a lot. And in physics term, it's really just the ability to do work. And that kind of makes sense. If you're tired, you don't have a whole lot of energy, you don't want to go to work. And if you have lots of energy, you can do a lot of work. Now you can store energy or have energy in a bunch of different forms: light, heat, sound, radioactivity, and in a way, mass can even be stored energy from Einstein's equals mc squared. And one thing that we also want to talk about is what it's measured in. The units for the energies are joules. Now, that should ring a bell because in work, we already talked about that work is measured in joules. It's Newton meter. And this is kind of how those things relate. Again, if energy is the ability to do work, well, if you have more joules of energy, you can do more joules of work. So let's jump right into the notes here. Again, there are the two that we're going to be getting into of mechanical energy is potential. Specifically, we're going to talk about gravitational potential energy and kinetic energy. So first off, potential energy is any energy that's stored. It has the potential, when released, to do work. There are many ways that you can store energy. For example, a rubber band. If you've ever seen one of those little planes where you wind up the propeller with the rubber band storing that energy, okay? And to spin it, you have to do work. All right? Springs, like in a mousetrap, you pull it back, and there's lots of energy stored in that spring. When released, will set off the trap. Gunpowder, all right, as soon as it ignites, releases a lot of energy stored in the chemical bonds. And even gravity, when you lift a book up over your head, all right, you are storing energy in its location above a surface. And for now, all we're going to really look at is the gravitational potential energy. Normally we describe that as GPE, and it's just the weight of the object times the height. So you can write it as the gravitational potential here, GPE, is equal to its mass times the gravitational field strength times the height. Remember that the weight is the same thing as the force of gravity, which is just m times g, which is why this works out that way. And the other kind of energy that we're going to talk about, but I'm not going to give you the equation to solve for just yet, and I do not want you to go looking it up, is the kinetic energy. Kinetic energy is just energy of motion. When you are moving, all right, that motion is storing some energy. So we started looking at this skater. And in this skater, or this simulation, we want to know where it had different amounts of certain kind of energy. So let's talk about the gravitational potential energy first. We can see that on this bar graph over here, that it reaches its maximum amount of potential energy at the highest point on the track that it reaches. So why does it have the highest amount of energy or gravitational potential energy there? It's because its weight, which is constant, all right, is as high above the bottom of the track, all right, as it can be. So therefore, it has the most potential to fall and do work. So if I want to calculate the gravitational potential energy of this skater at this point. There's a couple of things that we need to know. Since the gravitational potential energy is the mass times g times the height, okay, or in other words, it's weight times the height. Well, I need to know the weight, okay? That's the person's mass times g. So let's just give this person a mass of 50 kilograms. We also need to know how high they are above the ground, or at least the bottom of the ramp, because that's as far as they could potentially fall. And in this case, the ramp goes to the ground, so the height above that is 6 meters. So if we know all that stuff and we plug it into this equation, we get 50 times 10 times 6, and it gets a combination of 3,000 joules of energy. So then let's talk about the kinetic energy. So at the top, the skater has by far the most potential energy because it's stored as far above the surface as possible. But what we should notice is that as the skater descends and starts moving faster, they are moving the fastest at the bottom of the ramp. And that is where they have the absolute most kinetic energy. So they have the most energy at the bottom. So they have the most energy at the bottom because they're moving the fastest. So the question then is how much? Now normally this is where you would pull out another equation for kinetic energy, which we're not going to do. We want to know how to do this without using an equation, but using a relationship that we hopefully gathered from the video, or excuse me, from the activity. All right, notice how at this point, when the bar graph is this high, we have all potential energy, no kinetic energy, and we know at that point we had 3,000 joules of potential. Well, when it starts moving and it gets down to that highest, the most kinetic energy, it hits the exact same point. That means that just looking at that bar graph, we know that it should be equal to the same amount of potential energy when it was at the top, which was 3,000 joules of energy. This gets into what is known as the law of conservation of energy. The law of conservation of energy just states that energy cannot be created nor destroyed. All right? It can only change forms. In this case, we were seeing how it was changing forms from potential energy, energy stored in its position, and translating that energy into kinetic energy, energy of motion. But what about if we add friction? Okay, at this point, it was all frictionless. What if we actually go in and put friction into it? So let's find out. If we again start off with the skater up at 6, but we add in a little bit of friction. When we start to drop, we can see that it doesn't quite get as high on this side. And then it gets a little bit lower. And the amount of kinetic energy and the potential never reach back up to here, 3,000. So it would look as though if that energy is being lost. And if you ever ride a real roller coaster, you know that the second hill is never as big as the first hill. And the reason is that some of that energy is not kept in the kinetic and potential energy. Some of it is transferred to other forms of energy. In this case, we're using thermal energy as that third. And this should make sense that if you were to take your hands and move them, rub them together, you do that to warm up your hands. Well, what you're doing there is you are taking potential chemical energy stored in your muscles and in the sugar in your blood, and you are translating it into kinetic energy, the motion of your hands. Well, that motion is being lost a little bit. All right, to the friction in your hands, but also if you're cold and you start moving, that act of moving and using your muscles produces energy, all right, in the form of heat. All right. The overall energy, though, if you look back at our system here, is still the same. All right. It's just that that energy is being translated all into thermal energy. Right? And thermal energy is very difficult to recapture and turn into kinetic or potential energy. A lot of times it's called waste energy, because once things go into thermal energy, it's very, very difficult to get back. All right, so let's try a different tact on this. Let's just kind of tie this in with the work that we've done in the past. Let's say I rearrange this track. So I've added a ramp up to that first hill, kind of like a real roller coaster. You're starting on the ground, and a chain drags that coaster all the way up to the top. So the question is, if we had a person who had a mass of 50 kilograms, was lifted up 6 meters to the first hill, how much work was done? Well, we know that work is force times displacement. That chain had to apply a force equal to the weight of that person, which is 500 newtons. And the displacement is 6 meters. Not sure what's going on there. So we have a total amount of work done is 3,000 joules. So when that chain did work on that person, it actually gave it the same amount of energy as it had potential energy at the top of that hill, if you notice that. Also, that amount of kinetic energy that had at the bottom. So let's talk about the work energy theorem. So again, if you apply a net force over a given distance, it has a certain displacement, that's work. All right. And what you're really doing there is you are giving energy to that system. All right. By lifting it up, you're giving it gravitational potential energy. If you're pushing it forward with a constant force, it's accelerating, giving it kinetic energy. But the work energy theorem just states that the amount of work that is done is just equal to the amount of energy added to the system. And that's the real definition of work that we want to have. That work is just adding energy to a system. All right. So that's pretty much all we need to discuss for now with energy, how potential energy and kinetic energy relate, how work and energy relate. So you're going to use these then in the questions that follow in Canvas.